Hello everyone, I'm Paul and today we're solving problem 3508, implement router. This is a medium one that might seem tricky, so next I will show you how to solve this visually and then we will go with the code. This is a very long description, you can read this if you want, but basically we need to implement the router class. For this we need to build some data structure first, and then we need to implement three different methods: add packet, forward packet, and get count. So we receive packets in the form of source, destination, and timestamp. Each packet is unique, and each packet contains these three variables. And each time we call forward packet, we need to remove one packet from our list of packets. And we need to follow the first in, first out order. What this means is we need a queue. In case you know how queues work, we have a list and we add elements from the right and we remove elements from the left. Okay, so the first value that goes in is the first value that goes out. Okay, this is a queue. So we will call our queue all, and this is initially empty. So when we call add packet, we receive a packet in the form of source, destination, and timestamp, and we can add this packet to our queue. Now the thing is that every packet has to be unique. The first thing that we need to do when we receive a packet is to check if we already have it. And if we have it, we have to return false. So where can we store unique values? And the answer is in a set. So we will have a set, we'll call this unique, this is initially empty. And now every time we receive a packet, we check that we don't have this packet in our set. And if we don't have it, we add this to the set and we add this to our queue. And each time we call forward packet, we remove the first packet from our queue and the corresponding packet from our set. Now when we initialize this router, we have a memory limit, which is the maximum number of packets that we can store at any given time. So this is very important also. We'll have a variable which we'll call mx, and this will be the memory limit. So when we receive a packet, first we check that we don't have the packet in our set. Then we check that the amount of packets that we have is not equal to the memory limit, to the maximum amount of packets that we can have. And if the size of this is equal to this, we need to pop the first packet from here and we pop the corresponding packet from here. Now if the size for this queue is smaller than this, we can just add this here and here. Now this is overall simple logic, but the hard part comes here. We need to implement this method, getCount. For this, every time we're given a destination, start time and end time. So we need to return the amount of packets that we have in this destination, which are in between these start and end times. Now the problem is that we only have these data structures. We don't have a way to check for packets in destinations efficiently. So we're given a destination and we need to know which are the timestamps corresponding to this destination. So this looks a lot like a map where we have destinations as keys and each value is an array or a list with every timestamp for the corresponding destination. And this is very important, this is in the constraints. We know that queries for add packet will be made in increasing order for timestamp. What this means is we don't care about maintaining the right order for timestamps all the time. We can just pop the first element from our queue whenever we need to, And similarly, we can pop the first element from the corresponding destination whenever we need to remove some packet. So this is also a queue. And what this means is when we call forward packet, for example, we are removing the first element from all, and then we are going to the corresponding destination in this new map that we have here, and we remove the first element also. And for example, if we are trying to add a packet and we don't have the packet in our set for unit packets, and we have reached the maximum amount of packets, meaning the size for all is equal to the maximum, and we need to remove a packet from here, well, we also need to remove the corresponding packet from here, okay? So now with this map, we can solve this method. We are given some destination and start and end times. So we go to the corresponding destination in this map, and here we will have an array with timestamps. So when we call this, we are given some destination, let's say it's this destination, and we need to return the amount of timestamps that we have in between start and end times. Let's say start is 9 and end is 11. This means we need to return 3 because the left bound is 9, the right bound is 11. Here we have 3 timestamps, so in this case, for this method, we just return 3. Now the thing is that this array might be very, very large. We can't just iterate this from left to right because this requires a time complexity of big O of n. So we need to think about something more efficient. The key here is to run a binary search 2 times. One for start time and the other one for end time. So first we run a binary search with 9 as a target, and we will get this, meaning index 0. And then we run another binary search with 11 as a target, and we will get this, meaning index 3. And these are our 2 bounds. So we can just return right minus left, meaning 3 minus 0. And this is how we can solve this in low n time complexity. So as you can see, there's a lot going on in this problem. The first 2 methods are quite simple and this one is quite tricky. So with this in mind, let's go with the code. We are given this initially, so we can remove this part and we start up here. And first we have 4 variables. mx, which is the memory limit, all, which is our deck, unique, which is our set to store unique packets, and now we have our map for the last method. We will call this dest t for timestamp. This is a default dictionary with a default value of a deck for every key. And now for this method, add packet. First we can take a key, which is a tuple, with source, destination, and timestamp. And the first thing we need to do is to check if we already have this packet. So if key in self.unique, we just return false. Else, this means that we need to add this packet. But first we need to check if the length of self.all is equal to self.mx. We need to remove 1 packet. So we pop the first one, self.all.pop left, and this will give us 3 values, S, D, and T. And now we can remove the corresponding key from the map, so self.unique.remove a tuple with SDT, and self.dest at the current destination dot pop left. Remember that this is also a deck. And now we are ready to add the new packet. So self.all.append the key, self.unique.add the key, and self.dest at the current destination dot append timestamp. And if we add a new packet, we need to return true. So now we are here in forward packet, and the problem says that if we don't have any packet, we need to return an empty array. So if not self.all, we just return an empty array. Else we pop the first element from our queue or deck actually. So self.all.pop left, and this will give us three values, S, D, and D. And now we can do the same as before. Self.unique.remove SDT and self.dest at the current destination dot pop left. And the problem says that we need to return S, D, and D. Now we are in get count. This is the hard part. First we have an array which is self.dest at the given destination. And this is an array of timestamps. Here we need to implement two binary searches. So the left bound will be the first binary search. We can do a binary search like this in Python. Bisect left. And first we have the array. And next we have start time. This is the target. And we are doing something very similar for the right bound. But instead of using bisect left, we are using bisect right. Here we have the array, the same array, and end time. Now we can just return right minus left. So this is it for the code. I think this is right, so let's submit this and see if it works. As you can see, this works and it's efficient. Here, time and space complexity is big O of 1. Here it's also big O of 1. Here it's also big O of 1. And here, every time we run a binary search, this runs in log n time complexity. But the problem is that we are running a binary search on a deck every time. And there's an issue with indices here. So overall time complexity for this will be big O of n instead of log n. So there's a way in which we can solve this. Instead of having index here for every key in this dictionary, we can just have a list. So now this is a list, and every time we need to remove one element, for example here and here, instead of removing the element, we can have another data structure. We will call this self.off for offset. And this is a default dictionary with a default value of an integer for every value, for every key, sorry. And here, instead of removing the element, we can say self.off at the current destination minus equal 1. Sorry, plus equal 1. And we do the same down here. And now here we can add an argument. The third argument is the start point. So we can have a new variable here. We'll call it start. And this will be the offset for this destination. So this will be self.off at destination. And the third variable here is start. We are doing the same down here. And now this runs in log n time complexity, so this should be a little bit more efficient. Let's submit this and see if it works. And as you can see, this is very efficient. There's a difference here. So this is it for the code. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.